The goal of this presentation is to share with you guys our experience while working with Apache Ignite for the past few years and the lessons we have learned so far. About myself, I'm a software backend developer at iFood. I work with a team called Connection, and we are responsible for integrating and delivering food order events to restaurants and other external clients. About the agenda of this presentation, we are going to basically talk about our experience, the issues we had to solve and why we chose to use Apache Ignite, our first architecture solution that we came up with, and our journey with improving that solution and solve some problems along the way, and also our process of migrating our cluster to Kubernetes environment. So for those who don't know a little about the company, giving an overview of iFood, we are today the largest food tech company in Latin America. We are basically a food delivery app that's a consumer-facing application, but also we cover the whole process of food delivery, from the ordering of the food to the integration to the restaurants and also the logistics of food delivery. We are integrating today over 300,000 stores on 1,700 cities. We process around 65 million orders per month, which in turn generates over 500 million order events per month. So we work processing those events and delivering those and integrating those to the restaurants. This is our tech radar. This is an assessment that we do inside the company to keep track of all the technologies we are using as default for applying on solutions inside the company. Today, Apache Ignite is on trial, and this presentation is part of the work to make this technology more generally adopted on the company. So like I said, I work together with a team called Connection. We try to integrate and deliver our events to external clients. And one of the solutions we have for achieving this is polling API. So restaurant devices will regularly poll for events every 30 seconds by hitting a endpoint on the API. And for every event they receive on that request, they will also send acknowledgments for those events receipts, so that they will not receive that event again on subsequent polling requests. That's why the acknowledgments for. And also we work on other real-time solutions like webhook integrations and also a pub/sub solution using MQTT. So why did you choose Ignite for the polling solution? First of all, we started working with a Postgres database for indexing those events and implementing the solution. But it started to get performance-wise and scalability was getting a little difficult to solve with Postgres database. So Apache Ignite came as almost an obvious choice in that matter. Because it provided us with performance by being an in-memory data grid, and also because it was partitioned, it also solved the scalability for us really well. So, and also on top of that, it helped us maintain a similar architecture and modeling solution because it provided us with distributed SQL queries. So it was a very good choice, and it matched very well our solution at the time. So some of the features that we used to implement that solution using Apache Ignite was obviously we use partitioned caches for events and acknowledgments to provide us with better scalability. Third-party persistency with Postgres databases. This was, for us, Ignite was something new, so using third-party persistence was easier. So we chose to start with that to begin with. We also use affinity key mapping and distributed SQL with collocated joins so that we could have more performance queries running on the cluster. We use a lot of data rebalancing process because we have to perform rolling updates on the cache. So this was something that helped us keep runtime of the cache. We used it as an embedded database, and the implementation was made in Kotlin. This is an example of the modeling of the polling solution. We have the event, which is the primary model of the solution. The event key is affinity key mapped by the event ID, and an example of the acknowledgment model of the solution. You can see here that the acknowledgement is also key mapped by the event ID, and this will make sure that every acknowledgement of an event will be partitioned in the same partition that the corresponding event. So this will make this will improve performance of the polling query because it will be a local join, collocated join. So this is the polling query. Basically, when you do a polling request, you run a query that will search for every unacknowledged event of that device. So if the device hasn't sent an acknowledgement for the event, it will receive that event on the polling request. And after it acknowledges the receipt of that event, it will not receive the event in the subsequent requests. So basically, that's how the solution works for the polling. For the first solution we came up with using Apache Ignite, we had a single service, which was an embedded Ignite together with a Spring application. This was almost 4 years ago since we started to work with Apache Ignite. That application was responsible for consuming and indexing events on the cache by processing a AWS SQL, also exposing polling API endpoints and acknowledgement endpoints, and also performing cache operations like data cleanup and the persistent backup data loading, which was a third-party database. It was using at the time as infrastructure Jenkins CI/CD pipelines for deployments and chef cookbooks. It was using rolling deployments for the updates of the application. The services would run on AWS EC2 instances and AWS EOB. It was using a implementation that we had on AWS EOB Services Discovery. From that first solution, we started having some issues that came up with how it was architectured. So first of all, it was very difficult to scale automatically the application using metrics from like resource usage and requests per second, because the cache data nodes was part of the application. So historically, data nodes are hard to scale up and down dynamically. This would lead to unoptimized usage of the resources. It was also hard to maintain because every deployment was a cache deployment again. This will trigger data rebalancing and would affect the overall performance of the application. So every evolution of the solution was had a very high impact on the performance. We had to do rolling deployments at the time, so we couldn't have more control of the deployment process, like implementing some other type of strategies like canary deployments or other types of deployment strategies. And we also had some problems on using the ELB Service Discovery API because we were reaching some quota limits on that API, and because of throttling, we had some problems using that implementation. So from that initial solution and considering the problems we are having, we started to think of a solution for that initial architecture. So our first thought was to separate the cache from the application. This would improve our most of the problems that we had at the time, which involved deployments and scaling. And also we would improve infrastructure support by migrating our Ignite cluster to Kubernetes environment. This will lead us to 3 independent deployments, a worker application that would consume events from the SQS and index them in the Ignite cache, an API to expose polling acknowledgments endpoints, and a cache server to hold data and perform cache-specific operations, like data cleanup and persistent backup data loading. Our first decision that we had to make was decide over using thin clients or thick clients. We started to make some tests to see which one would better fit our solution. At the time, thin clients were very limited. This was a very long time ago, so we were using an old version of Apache Ignite. At the time, they were the thin clients implementation were not aware of data distribution. They had very limited access to the cluster API, and communication between the thin clients and the cluster was not very efficient. So because of that, we ended up choosing a solution using thick clients. Performance was very important for us since delivering order events to the restaurants and other stores in almost real time was very important. So any delay on that delivery would cause us a lot of problems. So performance was the key here for us. So choosing thick clients at the time was mainly because of performance. So this is our architecture for solving the solutions that we mentioned before. So we decided to separate the clients from the cache using thick clients, and which would make us end up with separate deployments between service and cache nodes. We would have more controlled deployments of clients nodes using canary deployments, which was something that we were implementing on the company. The cache nodes will be isolated from the application, so we will have less deployments, would be very less frequent on the server. And now the work in the API applications will scale independently, so we can optimize resource usage. It can scale on demand. And persistent backup is loaded from the cache server from a third-party persistent database. So having that proposed solution for improving the first initial architecture, we started to migrate from that old infrastructure to the Kubernetes cluster. The first decision we had to make for migrating to Kubernetes was the workloads of the application and the server nodes. The client nodes, of course, are regular applications, even though they are part of the cache, the topology of the cluster, but they work just like a regular application. So we decided to keep them as Kubernetes stateless deployments. And the data nodes, we decided to go for stateful sets, even though we were not using native persistency. We chose to keep them as stateful sets because we really need to have ordered automated rolling updates. That was really important for us to keep a good control over the data rebalancing process during rolling update, during a deployment, or any kind of update of the cache. So this was really important for us, and stateful set was something that provided that for us. So On that subject of stateful sets and ordered rolling updates, what we really needed was to have a good control over the rebalance process. So we achieved that by implementing readiness on top of the rebalance process. So readiness state of the pod is only reached when the rebalance is complete. This is performed by a custom endpoint on the application, the cache node application. So when we are rolling out the cache, pods that are getting updated does not enter the ready state until the rebalance process on that pod is complete, in order to advance to rolling the next pod. So this will guarantee us that we have good control over the rebalance process, and we don't have any problem like losing data or having some problem during rebalance. Liveness probes are disabled. This is required to avoid restarting of the pod while the rebalance operation is still ongoing. This is because we don't have control over the rebalance operation. It can take some time or not. So if liveness probes fails, Kubernetes will restart the pod, so we can allow that to happen. So liveness probes are disabled for the cache pods. This is an example of the rolling process, the rolling update of the pods. This is just an example to node cache with very little information. You can see that the rolling update of the pods takes a little over 1 minute on this example. This is enough time for the application to start up, finish up the rebalance process for that pod and enter the readiness state, and then the rolling update process goes on to the next pod for the update. The next decision we had to make was on service discovery, how it would be implemented on the Kubernetes cluster. At the time, we had to use the iFood application Helm charts that we supported at the time. So something that we're used to use was headless service discovery. So we decided to go for that. For those who don't know, headless service is just like a regular Kubernetes service, but it is not assigned an IP address. So it will work just like a DNS record for the pods. So performing DNS lookup on the service hostname, it will return all the IP addresses of the pods instead of load balancing the request to a single pod. So it works just like a DNS record, and service discovery implementation on top of that is really straightforward. So since we had already knowledge and support for headless services, we decided to go for that type of service discovery using Apache Ignite. This is just an example of how one would do service discovery using headless services. The code is in Kotlin, but is also supported for Java. It's pretty straightforward, like you can see. So it's nothing really difficult to do service discovery using headless services on Kubernetes. So having the proposed solution and the migration to Kubernetes, this allowed us to have a solution more closely to what are the development patterns adopted inside the company. We are using now GitLab CI pipelines, Kubernetes applications with Helm chart support for deployments. We support canary deployments for the applications, the worker and the API. And we support monitoring with Prometheus and Grafana. So this is, like I said, part of the work to have Apache Ignite more generally adopted inside the company. And it's still ongoing work. So we're still trying to define it better inside the company. So we had some lessons learned while migrating the cluster to Kubernetes. It was not so straightforward. First problem we had was problem with the cluster autoscaler, the Kubernetes cluster autoscaler. It was killing cache pods to reschedule them in other nodes. This is a regular application inside a Kubernetes cluster in order to optimize and scale down the Kubernetes cluster and optimize resource usage. This is, of course, a regular thing to do with stateless applications. So when you are working with stateful applications, it's a good thing to do to annotate them with the safe to evict annotation. This will make the Kubernetes cluster autoscaler ignore those pods when performing this kind of operation and avoid killing stateful applications. But when we did this, it was still not 100% effective. We started to figure out why was that, because it was not something that we expected. After some research, we discovered that because we were running our Kubernetes cluster on AWS, there was something on the AWS environment that's called the availability zone rebalancing. It is a process where the AWS will reschedule nodes to keep the numbers balanced between the availability zones that are configured in your cluster. This is active by default, so and because it is not a regular Kubernetes operation, it's part of the AWS environment, then it will ignore every annotation on the pods. So because of that, our cluster was still killing our cache pods and bringing us a lot of problems. So the solution for that was to create a nodes cluster group specific for Apache Ignite. We would run the Apache Ignite pods using node affinity on that cluster group. And just for that cluster group on Kubernetes, we would disable the AZ rebalance process. So we would not be affected by this issue. And this solved the problem for us. And we had very good uptime of the cache since then. Just to finish, to show you guys some of the results, this is the Ignite cache that we have on production right now. It's not very big cache, but it's really critical for us. So it's really important to have a resilient cache. And we have 7 pods running with 175 gigabytes of total cache memory. This is some of the example of the node capacity and the pod requests that we have right now. And some of the information that has each pod. This is an overview of the entire cache. We reach up to 50 million event entries and 30 million acknowledgement entries on the cache on peak times. Those entries have time to live, so they are deleted after some time. That's why the total entries on the cache is variable over time. This is the cache write rate, a snapshot of about 24 hours. We reach over 60 million events processed and 90 million acknowledgements on snapshots of 1 day that will be processed and indexed on the cache. This is an API overview. We reach up to 700,000 requests per minute on peak hours. We are a food delivery application, so we have peak on dinner and lunch, basically. So, but we also have a load test that runs on the application, and we reach up to 1 million requests per minute during those load tests. As you can see here, response time is really low. It is really important for us, and this is why Apache Ignite has been used by us for a very long time. it's very efficient, it scales very well, and the solution for us is it fits perfectly for this architecture that we proposed. This is an example of the dynamic scaling that I mentioned before. As you can see below, you can see the curve of the request per minute over time. And on the top, you can see the scaling of the application. It follows just the demand on the request per minute on the API. So the dynamic scaling will improve resource usage on the application. It was something we could not do before in the first solution, and the improvement brought this benefit for us. So a little about the next steps. We pretend to improve the support for Ignite on the company, so more people can start using it with a lot of performance. We intend to bring automated blue-green deployments out of the box to avoid downtimes. It's one of the problems we have right now. Performing Ignite version updates or Kubernetes cluster updates are really difficult to do while running stateful sets on the cluster. So having blue-green deployments makes that easier for us. We are going to try latest versions of the Java Thin Clients implementations, which are now partition aware and are much more efficient than the past versions. So we intend to do that. And also we are trying to implement a cluster segmentation detection and recovery strategy for the cluster, so you can have automatic recovery from those types of problems. And that's it. Thank you very much. Here's for everyone that wants to contact me, feel free to reach out. And I'm sure that there will be some questions. There will be a Q&A session right now, and I'm ready to answer them.
That was Henrique at iFood talking about their installation of Ignite there. So that was a great talk. Thank you. It's fascinating to hear about these deployments that, there's no way anyone would know about this if you hadn't talked about it. And from a European point of view, I'm sure I speak for many who would like to say we haven't heard of iFood, although we do have equivalent companies here as well. But it's fascinating to hear about these companies just in general and how big iFood is and how many transactions you have and the scale you're working at. It's great to hear. It's kind of what you're doing and how you're kind of using Ignite to do that. So I don't see any questions coming into the chat, so it's not too late. By the way, if anyone has questions, we can still ask them. But I do have a couple here that we've kind of thought up within GridGain. So the first one, I think it's something I talked to you about when we did the dry run before. It's like, so you chose to use your own service discovery mechanism rather than one of the built-in mechanisms. Can you talk a little bit about why you chose to do that?
Yeah, actually, like I said before, with the initial solution, we already had our own implementation of service discovery, which would rely on the ELB, AWS ELB API for service discovery. And when we were migrating, we were looking at just the Kubernetes-Service Discovery implementation that is provided in the Apache Ignite code base. And because our Helm charts did not support the configuration required by that service discovery, we chose to use our own implementation using headless services. And it was just because of that at the time we're also used to the service discovery interface, so we were comfortable by implementing our own version. But after we had our talk in the driver, of other service discoveries, and we actually realized that it was also possible using an implementation that was already provided. So the key here is the headless service configuration, and it is compatible with the regular service discovery provided by Ignite. So regardless of the fact that we implemented our own version, it is also possible using the provided code base. So it was something we did not know at the time.
I mean, it's good to know Ignite has that kind of flexibility anyway, right? Like
yes.
So, Hinav, I apologize for mangling your name, asked the question. I'm not completely sure I understand it. How did you come up with kind of pod memory or cores? I guess it's coming. How did you size your cluster? How, you know, did you decide to have many small machines or fewer big machines? How did you come at that kind of your current deployment?
Yeah, the sizing of the pods, the pods specifically, is something that we did a lot of experience. We tried a lot of different configurations and really chose something that would better fit our use case. And we also chose to have small pods because of the time to perform data rebalancing. So we from our experience, we realized that it is better to have smaller pods and an increased number of them instead of having just big pods, and this would lead to a lot of time between rebalance between the pods. So it was something that really was an issue for us. So that's how we chose those numbers.
So did you consider something like using native persistence as a way of kind of keeping uptime?
Yeah, actually, we haven't had a chance to work with native persistence yet. Like I said, we use third-party persistence. We chose to go for that because for at the time it was easier for us. We didn't have a lot of knowledge of Apache Ignite at the time. We were just starting with it, and we are still working in our learning process to work with native persistence. So we haven't had a chance to work with that yet.
I mean, honestly, this is a common pattern that people use. They kind of start using minimal APIs in Ignite, and as they grow more comfortable with it, they kind of start using kind of more and more. So I think, you know, what you're doing is fairly common. So so maybe this will end up being the last question. We have a question from VJ here. So kind of related to the last question about kind of persistence and rebalancing and so forth. So how do you load your data into Ignite at startup, and how long does it take?
Yeah, we just load the data on if you have a whole cluster failure or a downtime for any reason, like some type of maintenance process. When we do that, the first pod to start up will realize that just starting up a new cache, then it will start the backup data loading. It will just run a regular query on the underlying database and load the data with data streamers inside the cache. So this process is really slow. We have a lot of data in our database because, like I showed you guys, we have a huge amount of events going through the service during the day. So what we do to improve performance is to load up just a little snapshot of that of about 30 minutes or so, because since we are almost real-time event delivery platform, we don't have a need to load the entire database. So just the most recent ones are enough for us. For now, it is taking about between 5 to 10 minutes, depends on the time of the day. Like I said, the amount of events and acknowledgments on the cache will vary over time. So this will depend, but it's really efficient. It's just really fast, so it's not a problem for us.
So great to hear. Well, I think we'll call that a day on the kind of Q&A. I don't see many more coming in. So any kind of final words before kind of move on?
No, just it's been a really good experience presenting here at the Apache Ignite Summit. I hope you guys find the presentation useful and interesting. So hope it is helpful.
Definitely, kind of really appreciate your time and your energy, and I'm glad you've been successful with Ignite, and wish you continued success. Thank you again.
All right. Thank you, Stephen.